Imagine a future, right, where our devices aren't just, faster, but super tiny and barely sip power. What if the key to that future, the real key, is hidden in how our gadgets store information right now? Well, today we're going deep on a really fascinating bit of science. There's this new way researchers have found to control magnetism, like really precisely, in these incredibly thin materials. They're using something called CrPS, and it sounds like this could genuinely change things up in tech.
Yeah.
So our mission for you today is to figure out why this is such a big deal. We want to unpack how it can lead to memory, other electronics that are way faster, smaller, and, crucially, more energy efficient.
Yeah, and what's really interesting is where this is coming from. We're looking at research that just came out in Nature Materials. The paper's called Atomic Magnets, CrPS for Future Technologies. And it pulls together work from scientists at, well, several top universities. It really feels like it's setting the stage for something new.
Okay, before we get into the CrPS itself, maybe let's set the scene a bit. How does magnetism work for memory now? Like, in our computers, how do those tiny magnetic bits actually hold the data?
Right. Good place to start. So fundamentally, digital memory uses these tiny, tiny magnetic regions. Think of them like microscopic switches. Each one can be switched on or off, representing a 1 or a 0, a bit of data. The real challenge, though, and it's been a challenge for a long time, is controlling these switches precisely as we try to make everything smaller and more efficient. And that brings us to this tricky thing in material science called exchange bias.
Exchange bias. Okay, that sounds complicated, is it?
It definitely is. It's a force that influences these magnetic zones, which is useful, but the problem is, historically, it's been super hard to actually look at it, let alone control it. You see, it usually happens at the boundary, the interface between different materials layered together, and these interfaces, they're often hidden and, frankly, usually kind of messy or flawed.
Ah, okay, so you're trying to control something precisely, but it's happening at this messy, hidden boundary between layers. I can see why that's tough.
Exactly. It makes getting that fine-tuned control really, really difficult.
So this messy interface problem has been a headache. But now, these researchers, University of Edinburgh, Boston College, Binghamton, they've found what they call a simpler, more elegant solution. What is it?
Well, instead of stacking different materials, which leads to those imperfect interfaces we talked about, the breakthrough is using just one material, CrPS₄. That's CrPS₄. It's a type of semiconductor, and it's incredibly thin. We're talking just a few atoms thick. And the amazing thing they found is that you can get that same kind of magnetic control, that exchange bias effect, within the CrPS itself.
Just within the single material, so no need for layering different things.
Precisely. You bypass the whole messy interface problem because the control mechanism is inherent to this one material.
Wow, okay. But, hang on, if it's only a few atoms thick, how on earth did they even see what was going on, let alone control it? That scale is just mind-boggling.
It really is. And this is where the really cutting-edge techniques come into play. So what happens is, in these ultra-thin flakes of CrPS, just the thickness itself causes different regions to form naturally, regions with different magnetic properties. To actually see this, they use something called nitrogen vacancy center magnetometry, NV magnetometry.
NV magnetometry.
Okay. Think of it like an incredibly sensitive magnetic microscope. It actually uses tiny sensors in diamonds to map magnetic fields at a really, really fine scale. They combine that imaging with some heavy-duty computer simulations, and that let them literally visualize how these magnetic regions formed, how they interacted, and how they shifted right at the boundary where the thickness changes, say, from 4 layers thick to 5 layers thick.
So they can actually see these boundaries within the material itself. Did that visualization also mean they could control it? Could they, tweak that exchange bias you mentioned?
Yes, absolutely. That was the next crucial step. They found they could essentially turn the exchange bias effect on or off within the CrPS.
Like flicking a switch.
Pretty much, yeah, like flipping a switch. And importantly, the research shows this control is repeatable and reversible. Dr. Elton Santos, one of the researchers from Edinburgh, used a great analogy. He said, the regions inside CrPS line up side by side like lanes on a highway. The border between them forms a perfect interface.
Oh, a perfect interface. Unlike the messy ones between different materials.
Exactly. Allowing us to study and control magnetic behavior with incredible precision. That perfect interface bit is key. Because it's naturally formed within the material, it doesn't have the defects and randomness you get when you stick two different things together.
Okay, that highway analogy helps a lot. It's like the material creates its own perfectly smooth lane dividers internally. So it sidesteps that whole decades-old problem of messy junctions.
That's a really good way to put it. It's inherently cleaner control. The material itself is kind of doing the hard engineering work for you, providing the stable, predictable platform.
Fascinating stuff on the how.
Hmm.
But let's get to the so what. If you have this level of precise, clean control over magnetism at the atomic scale, what does that actually mean for technology? What could we build with this?
Right, the implications. Well, first, it obviously helps scientists understand magnetism itself much better. But
Mhm.
beyond the fundamental science, it really paves the way for potentially much smarter, smaller, and definitely more reliable magnetic devices.
Like what, for instance?
Well, the obvious one is memory. Think ultra-compact memory chips. You could potentially store vastly more information in the same space or the same amount of info in a much, much smaller space. But also things like sensors, maybe sensors that you could reconfigure on the fly for different tasks. And looking further out, it could even be relevant for things like quantum computing, where precise control over quantum states, sometimes magnetic ones, is absolutely essential.
Okay, so potentially transformative stuff. But is CRPS itself practical? Sometimes these amazing materials only exist under crazy lab conditions. Is this something we could actually, manufacture?
That's a really important question, and one of the promising things about CRPS, according to the research, is that it's relatively stable in air.
Oh, that's a big deal.
It is, and it's apparently easier to work with compared to some other exotic 2D materials that might need vacuum chambers or, incredibly complex handling. So yes, it seems more practical. It has a better shot at moving from a lab curiosity to something used in real applications. Dr. Santos summed it up nicely again. He said, this breakthrough opens a window into the invisible world of atomic-scale magnetism. He called it a transparent and reliable platform to understand and engineer magnetism at the atomic scale, and that it opens the door to a whole new class of magnetic technologies.
Seeing and controlling the invisible, basically, is pretty amazing. And just for context, this research we've been discussing was published June 12, 2025 in Nature Materials, and it had backing from UKI, the NSF in the US, and the Royal Society. So wrapping this up for you, the listener, the big takeaway here is that by getting this incredible control over materials right down at the atomic level, specifically with this CrPS₄, we're genuinely getting closer to a future of revolutionary electronics, devices that could be faster, smaller, and way more efficient than what we have now.
Yeah, it really makes you think, doesn't it? And maybe here's something to mull over. We're now figuring out how to engineer these perfect interfaces and control magnetism with this incredible precision. So what other forces, what other invisible aspects of nature operating at these tiny scales might we soon learn to see, to understand, and maybe even engineer for technologies we haven't even imagined yet?